right. Thank you all for coming. I'm Helen Sages.
My name is Claire Hu.
I'm Pratik Jane.
I'm Melissa Kai.
And I'm Anita Shipman. And we spent the past 4 weeks researching disposable paper-based sensors to detect water leaks.
So, our main goal for this project has been to design and fabricate an affordable and disposable leak detection system that can be used on roofs in houses or commercial and industrial buildings. We will talk about how our initial objective was to determine the volume of water leaked and how it changed to become identifying the exact location of the water leakage. For our purposes, we decided to use metallized paper as the main component of our sensor system, and metallized paper is commonly used for packaging as shown in Figure 1. This material is really just regular paper with a layer of metal ablated onto the surface of it, and because of this layer of metal, the substance has a latent charge within it that can be harnessed as a capacitor and can be used for innovations such as the armored keypad shown in Figure 2, and also, of course, for our paper-based sensors. So why did we embark upon this mission? Water damage accounts for 20 to 25% of all property loss costs in the United States every single year. So if we design a successful system that can identify the problem at the onset, we can significantly reduce the risks of incurring costs to the user. A metallized paper system is especially suited for this purpose because metallized paper is extremely inexpensive. It only costs under $1 for every square meter of the material, and it is also easily scalable because it is easy to mass produce.
So the underlying theory behind these paper-based sensors is capacitance. So what is capacitance? Well, capacitance is the storage of charge. So our metallized paper, when created gaps in between, created this electromagnetic field, and it has its own latent charge in the gaps. So when a conductive material is put within these electromagnetic fields or between the gaps, there's an increase in capacitance, and this capacitance can be very easily read by Arduino. Arduino is a microcomputer that can be hooked up to an actual computer and be read. The data can be read.
So here we see a general overview of the process that we took to create our sensors. First, we brainstormed ideas for the designs and drew them using SolidWorks, which is a computer-aided design program on the computer. After they were designed, we printed them out using a laser cutter, and here you can see some of the buttons that were printed out, ready to be tested, which is the next step. The sensors were all individually tested to find the one with the greatest sensitivity, and the one with the greatest sensitivity was then integrated into the Arduino circuit for our final product. So the first step, designing the different sensors, was we brainstormed a lot of different ideas for this, but our main goal was to find a sensor design that would have the greatest probability of having water land on a gap in the sensor, because the Arduino computer can only sense water leakage when the water lands on a gap. So in trying to find the best sensor for this, we changed different aspects of the design. In the first we changed the gap sizes. In the first image on the left, you can see that the distance from prong to prong is less than the distance shown on the second picture on the right. So that was the differences in gap size that we experimented with. And in addition to that, we also experimented with different shapes of the prongs. So on the left, again, you can see a rectangular prong shape, and on the right, you see a curved prong shape. And this created variability in the uniformity of the gap sizes. So after the designs are created on the computer, they were sent to a laser cutter, which then cut out the separate plates, and then we manually put them onto acrylic backing. And it was only when the sensors were physically made that we found some of our biggest design flaws. So our first designs were so large that the gaps were too large, and the water then could not even bridge the gaps, which meant that water leakages couldn't be read. So then since the size was too big, we scaled them down. Next, we found that some of our sensors had prongs that were too thin or too close together, as shown here, and thus made a design that was too flimsy and not durable enough for practical use. And finally, through the fabrication process, we found the most efficient way of using double-sided tape as an adhesive to mount the sensors onto an acrylic backing, which was durable enough for our uses.
So as Alyssa mentioned earlier, for our initial testing, we did a water drop test on each of the sensors individually. So we would drop water on each of the sensors from a uniform height of 10 centimeters, which was done to create some control in our experiment. And then once it was dropped, the capacitors were hooked up to an impedance analyzer, which would chart the change in capacitance when water fell on each of the sensors. And this data was taken down and then graphed. As you can see from this graph, the data followed a positive linear trend from water dropped on the sensor to the change in capacitance. And this is actually the graph of our final design, a rounded 1 millimeter thick by 1 millimeter thick gap and prong size. And this is also the point in which we changed our objective, as Claire mentioned earlier, to deciding where exactly the water was falling, as opposed to defining how much water was actually falling.
Okay, so here we have our final setup. Right here, this is the design that some of you might have seen in the demo room earlier. And as we've been saying, our design was changed so that we could accurately detect the specific coordinates at which the leak occurs. And that required a very specific type of fabrication process. So the process we described earlier was to cut all the way through the metallized paper, which created two separate comb-shaped pieces, which we then had to fit together by hand and then mount on a backing. But we found that that was not exact enough for the coordinate system that we wanted to create. So what we did instead was we used the laser cutter on a different setting, this time on the engraving setting. And the engraving setting takes off the first layer of aluminum to create the shape that you see left over on the aluminum part of the paper. So that creates a much more exact and much less labor-intensive way of fabrication. So the curved prong sensor that you saw before was actually doubled up. So we used a sensor on top as representative of x coordinates. So each prong of the sensor represented a row, x1, x2, x3, so on until x8. And the sensor behind that represented y coordinates, and each column was numbered y1, y2, up until y8. And once we had double layered the sensors and taped them on top of each other to create the square that you see here, we hooked it up to the circuit that you see above. And you see that there's the circuit, and then there's a breadboard with lots of wires in it. And there's the Arduino, the microcontroller, which we use to actually detect the capacitance changes. And you can see the whole setup here.
So the Arduino communicated with the computer using code over here. So some of the features of our code include all of the columns and all of the rows were printed in rapid succession with 100 millisecond breaks in between. Additionally, after all of the 8 rows and 8 columns were read, the whole grid was read. And the grid was updated every 5 seconds. So the grid would read if there's a leak, and if not, it would just print no leaks. And when there was a leak, it would print a leak. So what the user would see is the coordinates of where the leak was. Over here, you can see our code. What our code is basically is the use of tolerance. So when the capacitance goes over a certain level, it says there's a leak, and it prints out the coordinates.
Okay, so what Pratik just showed you was actually the code for one button, but since we had 8 rows and 8 columns, there were actually 16 different buttons that we had to write that code for. So that required a lot of testing because we had to change variables into those buttons. And it turns out that you can detect leaks individually. Say you can detect a single point leak, or you can detect a multi-point leak, which we have demonstrated for you here. So this demonstration, this picture right here, is what the user would see if there was a leak. And you can see that there are 4 different leaks in this example. And here we have a video for you of our final setup in case you missed the demo. Okay, so it might be a little hard to see because it's kind of far, but the person on the right is Alyssa, and she's dropping water onto our paper sensor. And yes, there we go. So the water just dropped, and it's on a bit of a time lag, but you can see that the scrolling on the right detects where the leak happens. So you see that she keeps dropping, and the previous leaks also keep logging because the way the system is designed, the leak alerts only leave once you've addressed the leak. And yeah, eventually the entire sensor will fill up and it'll reach its disposability point, after which point you'd have to replace it.
So let's take a moment to review our main goal again. This was to design and fabricate a disposable and affordable leak detection system that could be used in various types of roofings. So we believe that we have achieved this goal in our prototype of a leak system that detects the exact location of the leak, the water leakage. And some other successes that we've encountered include the fact that we chose the right material when it came to metallized paper. Metallized paper is disposable and it also is very inexpensive. Also, the entire unit itself is cost effective because the Arduino unit that you get in initial installation only costs approximately $40 or less. And then the only other costs that are associated with our system is the replacement of the metallized paper. One last success is that we managed to design a procedure that makes it very easy to fabricate our sensor system. So that means that it will be easily mass producible.
Okay, so our sensor has many further applications and many other directions in which we'd like to take it.
So if we had more than 4 weeks, some of the things we were looking into were creating a graphic user interface. So instead of reporting the coordinates of where the leak has occurred, we'd rather create a graphical grid, which would make it easier for the user to just visualize the grid and go to the leak. Additionally, we would like to create a phone application. So this would help the user detect leaks away from the detectors. So it would be on the go. And finally, in our project, we used the Arduino Uno. But we would like to use a different model for future testing, which is the Arduino Yun. And what this does is it connects to the Wi-Fi, and when it connects to you can send data over long distances.
So Pratik's been describing better user interface, but we'd also like to describe other further applications. So our current system has only been tested for water leakages, but there are many other substances that leak which could pose potential hazards. We listed alcohol and petroleum here. And in addition, the pharmaceutical industry actually has a very big problem with leaking of pre-filled syringes, which can potentially be very harmful to health. And our exact setup can actually address that issue.
Finally, we'd just like to take a moment to acknowledge everyone who has helped us with this research over these past 4 weeks. Our project mentors, Dr. Aaron D. Mazzeo, Chuyang Chen, Shiyu Zhou, and Matthew Maroli. A special thank you to Chuyang Chen, who has dedicated much of his time to our research and helped us with the circuitry, and to Shiyu Zhou, who has dedicated a lot of his technical knowledge to us, as well as assistance with the Arduino Code, him and Matthew Maroli. In addition, we'd like to thank our advisor, Taylor Au, and our research coordinator, Edmund Hahn, the director of the Governor School of Engineering and Technology, Dr. Eileen Rosen, and the associate director, Jean-Patrick Antoine, and finally, all of the sponsors of the Governor School of Engineering and Technology, Rutgers, the State University of New Jersey, the Rutgers School of Engineering, the State of New Jersey, and all of the additional sponsors. Thank you.
We open the floor for questions.
So you said this will be essentially to these scales. How big can you make it, and would it still be as precise?
Well, yes, it would be.
In the demonstrations that we showed, you see the one small square of the sensor, and in actual real-world application, you can take as many of those smaller squares as you need and just map them out for as long as you need, and they will each have the coordinate system, and you can input it into one large grid, and that can tell you where the leaks are.
And you still need Arduino for each one of those grids, or
You can actually hook up multiple paper sensors to a single Arduino. And the Arduino system that we were demoing before, the paper sensor, had 64 unique points, and it was a 10 centimeter by 10 centimeter grid. So you could make it as exact or as inexact as you wish for your particular project. Other questions?
I have a couple of questions. First of all, if you punch a hole accidentally in one of your areas, would it interfere with the other parts of the sensor? Secondly, if you paste this thing around your house or a room, to what extent would it create like Faraday cage type of mechanisms, such as drop cells and other signals that you sell?
Well, I can talk about the punched out. If you do puncture a hole into the sensor, first of all, it's very easily replaced because it is disposable and it's very cheap. But other parts of the sensor will work if you do punch a hole through it, since they're all uniquely wired with 8 different wires.
so
Second question.
As for the second question, that was a bit beyond the scope of our research. It wasn't what we focused on because the initial application that we thought of was putting it directly underneath the roofing of a house and under like isolated locations where it's more easily at risk of a water leakage.
It is definitely a good concern though, especially if we want to scale it up to industrial applications.
Any other questions?
Any other questions?
Do you think that oxidation of, I guess, whatever metal you use for the paper metal, would that cause an issue with your sensors?
The metal we used was actually aluminum, and it's been wet and dried so many times over the past week that we really don't think that that would be an issue because our sensors were initially designed to be single use, maybe double use. The one we were demoing, we've used probably 50 times and it still works. So, yeah.
Is the paper recyclable? And if so, is it as paper or metal?
That's actually not a question. So our mentor, Dr. Mazzeo, calls it biocompatible, meaning
It's not harmful.
it's
to
not
anything.
harmful, but it also doesn't degrade easily. So if that answers your question. Yeah.
I think you mentioned that the material is disposable, meaning like once it's used, you need to kind of dispose it and kind of reinstall it. But I guess another thing she just mentioned that you can actually reuse it, like by wiping it off. Is
Yeah.
it like what part of the product makes the need for disposal?
All right. It is disposable in the sense that it's not meant to be used over and over and over again over a period of years. We've only been testing this for a week or two, so we don't really know the long-term effects on the paper itself. So what the intention of this project is you're not supposed to have leaks very often, so hopefully it'll be able to be used for a while, and then once it is used, it will have to be disposed of because it's been subject to long-term exposure to the air and all of the other elements.
In addition, the demos we were doing were a few drops or a few milliliters, but if you put it, say, in your basement, that's probably a much larger scale leak, and the paper would probably be much more destroyed.
Additionally, the one of the problems we were having for using it over and over again was there's water residue in the sensor, and it's not that easy to get rid of the water residue. In fact, for testing, we actually used a blow dryer. I mean, if you want to, you can use a blow dryer. It's not going to be as effective. And since the material is cheap, it's just easier just to buy new sensors.
Any others?
Michelle?
How much,
Oh.
how much do you think your final model costs?
Final model costs? Well, I mentioned before that the entire Arduino unit, which is just the Arduino circuit plus the Arduino breadboard, costs under $40. And then depending on the size of the house or the building that it's used in, the paper costs only under $1 per square meter. So that is literally the only costs that are associated with our system.
And the Arduino cost is a one-time cost, so the only thing that needs to be replaced is the paper, which is under $1 per square meter.
Yes.
Will your sensor react to humidity causing false alarms?
That actually was part of the errors analysis. We didn't have enough time to fully test that, but it is definitely a concern. If you have a lot of humidity, that will definitely tamper with the system.
But then again, you could set the thresholds to different amounts if you know it's going to be installed in a humid location.
Thank you.
Thank you.
Thank you.